Alrighty, hello everybody. Welcome to chapter 7.2. We're going to solve systems again, but we're going to use the addition method. And that is one of our objectives, just learning how to use that, kind of reviewing it, because I'm sure you guys have gone over this before. And I really want to also reiterate that the graphic and corresponding algebraic scenario for when a system has one, no, and infinitely many solutions. Let's begin, though, with an example. If we had a system that looked like this, 3x plus 5y equals 7, negative 3x minus 2y equals negative 1. What we've learned previously is that we can solve one of these for x or for y, and we can substitute that value back in for x or for y into one of the equations. However, what's pretty cool that we can do with this one happens because of our x's. If you take a look at our coefficients in front of x, they're the same number, but they're opposite signs. This one's positive, this one's negative. So if I were to combine them together, what I end up getting is a 0. 3 minus 3 would just be 0 here, so I'd essentially eliminate, that's why this method's also called elimination, I'd eliminate my x's. And then if I do 5 minus 2, I get 3y, and if I get 7 minus 1, I get 6. So I get that y equals 2. When I substitute back into one of the equations, it's your choice. You can substitute back into the top or the bottom. It does not matter. I'm going to choose the bottom, though, because I'll multiply by fewer numbers. Negative 3x minus 2 times 2 equals negative 1. Negative 3x minus 4 equals negative 1. Negative 3x equals, add 4 to both sides, and I get 3, and I get x equals negative 1 when I divide both sides by negative 3. So it turns out that my solution here is going to be negative 1, 2. All right. And that's how substitution is done. We can write up some basic steps for this process because it's not always going to be this simple where they cross out automatically. So what we can find, I'm trying to say right, what we can write out are the steps. The first being, number 1, is that we need to make coefficients the same number but opposite signs. And typically, one coefficient, either the x's or the y's, one set of those will kind of lend themselves to be made into the same number a little bit more than the other. And we'll talk more about that as we do more examples. And then you must add the equations together. Substitute, oh my goodness, substitute, S-U-B-S-T-I-T-U-T-E, substitute, what are we saying, the value from step 2 back in. And then lastly, what we got to do is check. We can check our solutions by substituting those values back into the original system. All right. So let's get started with another example here. Let's try one that's a little bit less obvious. Let's try the system 2x minus 3y equals negative 7. 3x plus y equals negative 5. What I can do here is, remember from step 1, we want to make coefficients that are the same number but opposite signs. If you look at your y's are already opposite signs. The only thing you need to do still is make this bottom one a 3y. And we can do that by using multiplication. So if I were to take this bottom equation and I were to multiply both sides by a 3, here's what my new system is going to be. My top equation stays the same, 2x minus 3y equals negative 7. But on the bottom, I get 9x plus 3y equals negative 15. And oh my goodness, would you look at those y's now? We have exactly what we had in the last example, where we have a negative 3 and a positive 3y that are going to cancel each other out. And we add the rest of what we've got. 2x plus 9x is going to get me 11x. Negative 7 minus 15 is going to get me negative 22. I divide both sides by 11, and I get x equals negative 2. Fabulous. On to step 3 from our steps. We have to take this negative 2 and we have to substitute it back in. Substituting back into the top would make sense since that's a smaller coefficient in front of x. And I get 2 times negative 2 minus 3y equals negative 7. My first step here, if I just follow order of operations, I should multiply first, and I get negative 4 minus 3y equals negative 7. I should add 4 to both sides, and I get negative 3y equals negative 3. I divide by negative 3, and I find that y equals 1. So my solution should be negative 2, 1. And if we check that solution, let me do a different color here. If we check that solution back into our original system, we get 2 times 1 minus 3 times negative 2 equals negative 7. And we get 3 times negative 2 plus 1 equals negative 5. And when I throw these sides of the equations into my calculator, I do find that these work, right? 2 times 1 is 2, plus 5 is, oh, pardon me. Oh, I did the wrong thing here. This needs to be a negative 2, pardon me. Make sure you change this. I need to plug in the x right here, so 2 times negative 2. Here we go. That was bad math, my bad. And 3 times 1 needs to go here. 1, okay. 2 times negative 2 and 3 times 1. Now let's try that mental math again. So I get 2 times negative 2, which is negative 4, minus 3 times 1. Negative 4 minus 3 is in fact negative 7. That checks out. 3 times negative 2 is negative 6. Negative 6 plus 1 is in fact negative 5. That checks out. We are good to go. Moving on to yet another example. Doesn't hurt to see more than one of these. We will look at the system 5x plus 3y equals 9 and 2x minus 4y equals 14. So I'm making these just a little bit tougher every time. You'll notice now that there isn't as easy of a solution here. I can't just multiply only 1 now. What I'm going to have to do to tackle this is I'm going to have to multiply both the bottom and the top equations by something to create a coefficient that is the same number but the opposite sign. That being said, before I get into all that, I'm going to choose which ones I'm going to change. Right now, my x's don't have the opposite signs, so that's not very helpful. However, my y's do. My y's have a positive and a negative in front of them, so they're already the opposite signs. Now it's just my job to turn them into the same number. And we know from multiplication that 3 and 4 can both become the number 12. I can turn a 4 into a 12 by multiplying by 3, so I'm going to multiply the bottom equation by 3. I can turn a 3 into a 12 by multiplying by 4, so I'm going to multiply the top by 4. Once I've done this, my new system is going to look like this. 20x plus 12y equals 36. 6x minus 12y equals, what do we got? 30 plus 12, 42. Okay. And now when I do some math, I see that my y's are going to cancel each other out. I'm going to add these x's and get 26x. I'm going to add 36 and 42, and I'm going to get 78. Now, when I divide both sides by 26, I get x equals 3. So I can take this value for x and I can substitute it back into one of my equations. I'm going to pick the bottom because it has the smaller coefficient in front of x. It makes it a little bit easier. So I'm going to have 2 times, it's a different color there, 3, minus 4y equals 14. Okay. Now what I get is 6 minus 4y equals 14. I subtract 6 from both sides, and I get 8. I divide by negative 4, and I get y equals negative 2. So my solution should be 3, negative 2. When I double check those, just to be sure, however, I should get the following things. 5 times 3 plus 3 times negative 2 equals 9. And 2 times 3 minus 4 times negative 2 equals 14. If I do some mental math here, I get 15 minus 6 equals 9. That's true. And here I get 6 plus 8. 6 plus 8 is in fact 14. That's also true. Okay. Let's kind of recap graphically what's happening here. I want you to understand that for the following systems, the following things are happening graphically. We've talked previously about how, let's see, if we have Alright, so we've talked previously about how solutions to systems are the point of intersection. So we already know that if we have two lines, I'm not going to make these like actual equations, I just want you to kind of see graphically what I'm talking about. If we have any two linear equations, the point where they intersect is their solution, right? We're going to draw a little arrow and we're going to say that's the solution. And we could have, this would be the case of one solution. What else we could have is a set of lines that never cross each other, right? Perfectly parallel lines. And what we would say here is that there are no solutions because there's never going to be a point where these lines do this. These lines are never going to cross each other. There are no solutions. Let me use a little bit of color for this next thing. If I had, not sure, let me use this. So if I had a line, doesn't really matter what, if it was just a linear equation, and then I had another line exactly on top of that. I'm going to draw just another little color out, right? Where maybe I have one line in black and I have another line in orange. There are two equations, a system that has two equations that graph the same line. Then what's happening there is I have infinitely many solutions. So it's important to note that no solution and many solutions will give you linear functions that have exactly the same slope. One solution, the slopes will not be the same because they will be intersecting each other. Alrighty, that's kind of graphically what's happening there. Let's talk about the no solution case. So, oh, you know what? I want to tell you one more thing. No solution, algebraically, what this is going to look like would be if you do some math and then your system looks something like this. Let's say we got negative 4x plus 6y equals 3 and 4x minus 6y equals 7. When we do some math here, our x's and our y's cancel and we get 0 equals 10. That sounds strange because it's not true. It's a not true equation. So this is the case where we would have no solution. Infinitely many solutions, algebraically, looks like this. Let's say that we had maybe kind of the same sort of thing. If I had, let's say, negative 4x plus 6y, and then 4x minus 6y, but this time, let's say they're both equal to 0. These cancel, I get the equation 0 equals 0. That's a true equation. In that case, every value I plug in for x and y will give me a solution. That's because every value on this line and every value on this line will intersect each other. That's why they're all solutions. Okay. Moving on, let's talk about when we'll say example, and we'll title this example, no solutions. So kind of what I just showed you, but we're going to go through exactly what that'll look like. If I have x minus 2y equals 3 and negative 2x plus 4y equals 1, we'll take a look. Both of these have opposite signs. However, it'll be kind of easier to multiply the top by 2, and then that way I'll get my x's to cancel, and I won't have to do as much work. Actually, 2 will work no matter what. Anyway, doesn't matter. Let's get into multiplying. When I multiply the top by 2, write that step out. Multiply the top by 2, I get the new system, 2x minus 4y equals 6, and negative 2x plus 4y equals 1. It's important for you to point out that this system is equivalent to this system. Remember that in algebra, when I multiply both sides of an equation by something, I don't change it fundamentally. I only make it easier to work with. So these systems are equivalent even though they look a little bit different. All right, that being said, let's cancel. Again, you're going to see kind of a parallel happen here. My x's will cancel, my y's will cancel, and I get 0 equals 7. That is not a true equation, so what I can say then is no solution. Infinitely many might look like this. I have 2x, let me do my fancy bracket, 2x minus y equals 1, and 4x minus 2y equals 2. What I could do to solve this one is a little bit different, kind of interesting. You'll notice when we look at our x's and look at our y's, neither of them have opposite signs yet. Oh, okay. Right now, though, let's focus on getting them to be the same number. When I look at the top, I can see that I can turn my x's into the same number and my y's into the same number by multiplying by 2. However, I don't have any opposite signs. So the type of 2 I'm going to multiply by is going to be a negative 2. And when I do that, what I'll accomplish is getting opposite signs. Here's what I mean. My new system, once I've multiplied by negative 2, is going to get me a negative 4x, a positive 2y, and a negative 2. And then on the bottom, I still have 4x, and I have minus 2y equals 2. Now you can see that I have opposite signs with my x's, opposite signs with my y's, which is going to allow me to cancel them. And I get 0 equals negative 2 plus 2 equals 0. That is a true equation, so I can say I have infinitely many solutions. Again, if you're finished with your elimination, with your addition, and you get an equation that's not true, no solution. You get an equation that is true, you get infinitely many solutions. Alrighty, so what I would like to talk to you about now are some applications. We'll talk about maybe one word problem, and then I'll do another with you for a warm-up tomorrow. Alrighty, so I do have an application problem here for you. If you want to take a second and just write this down. If you want to pause the video, that's more than okay. I'm going to read through it, though, and then we'll start working it out. So, an airplane flying into a headwind travels the 2,000-mile flying distance between Chicopee, Massachusetts, and Salt Lake City, Utah in 4 hours and 24 minutes. On the return flight, the same distance is traveled in 4 hours. Find the airspeed of the plane and the speed of the wind, assuming that both remain constant. So let me draw a picture of what's happening here. So, when the plane was flying to Kansas, it was flying into this wind, right? Our plane, I'm not the best artist, so don't critique me. Our plane, there we go, was flying in the direction of the wind. They're kind of working against each other. And the speed that we can say here, the air speed and the wind, were working against each other in this way. the airspeed of the plane was happening as a result of subtracting the wind going against it. So I'm going to use A minus W to kind of represent the situation. This was the first scenario, the one that took 4 hours and 24 minutes. I'm going to kind of write that below it too. 4 hours and 24 minutes. Now here's the thing. We can say that that's 4 plus 24 over 60, but guess what? 24 over 60 is just 0.4. So what we really have going on here is 4.4 hours. All right. And then what we had on the way back, we still have the wind going the same direction, the same speed, but our plane was now getting pushed forward by it. So here's our plane, and it's getting kind of this extra help now from the wind. And so what's happening is the airspeed of our plane is happening as a result of adding the speed of the wind to it. The wind's helping it out. Here it was going against the wind, so the airspeed minus the wind was the speed of the plane. And now the airspeed, the regular speed in still air, without any help from the wind, got help from the wind, so we say A plus W. And this happened in just 4 hours. See, here's what we can say. We can set up two equations here using that 2,000-mile distance. The first equation we can write out is 2,000 equals this top guy here. A minus W represents my speed, and 4.4 is my time in hours. So what really happened here, 2,000 miles occurred when I flew at this speed for this long. So what I can say is 2,000 equals 4.4 times the speed, A minus W. And for the bottom equation, I can say 2,000 equals 4 times A plus W. And now what I can do is I can distribute out my 4.4 and my 4. And what I get going here is 2,000 equals 4.4A minus 4.4W. And 2,000 equals 4A plus 4W. And I'm going to write a little bracket around that because that's the system we're going to start with, and then we're going to work with it. So to start working with this system, like I've told you in class, if you ever have decimals in equations, you are more than welcome to get rid of them. And I think that's a good first step for us to take right now. If we have 4.4 and 4.4, it's very hard for me to understand how to make these two the same number. I'm having a hard time even visualizing that, frankly. So what I'm going to do to kind of help myself out is I'm going to multiply the top equation first by 10, and then that way I'm going to get rid of my decimals. And once I get rid of my decimals, this will be a much easier system to work with. So now that I've multiplied by 10, my new top equation is going to be 20,000 equals 44A minus 44W. And on the bottom, I still have 2,000 equals 4A plus 4W. All right. And now what we can see is going on here is my W's have the opposite sign. Remember, if you look back to your steps on how to solve these, that's very, very useful. To have the opposite sign already is very helpful. And the only thing we have left to do is to make them the same number in front, make them the same coefficient. And I can do that very easily by multiplying the bottom equation by 11. 4 times 11 will get me 44, and then I'd be able to cross these out. So let's do that. Multiply the bottom equation by 11. And my new system is going to start looking like this. I'm going to get 20,000 equals 44A minus 44W. And then when I do 11 times 2,000, I get 22,000 and 44A when I multiply by 11 and 44W when I multiply by 11. Now remember, our whole purpose for doing that was so that we could cancel out our W's. And now I get 88A equals, let's see, 42,000. And when I divide both sides by 88, I get, first let me show that I'm dividing by 88 because we're going to use this later, that my airspeed, the speed of the plane in still air with no influence on it, is 477.273 miles per hour. And I can take this, I'm not going to use this because I rounded off a decimal. I'm going to use my fraction, 42,000 over 88. I'm going to substitute that value in for A into one of my equations. This one has the smaller A value, so I'm going to throw it in there. And when I do that, I get 2,000 equals 4 times 42,000 over 88 minus 44W. When I do 4 times 42,000, I get 168,000 over 8 minus 44W, and I still have 2,000 over there. And so what I need to do next is subtract 88, pardon me. Subtract 168,000 over 88 on both sides. 2,000 minus 168,000 over 88 equals negative 44W. I can divide both sides by negative 44. And it's okay that things look a little bit messy right now because we can just do this whole thing in our calculators and we'll get the same answer, but it's important that you keep these fractions improper so that you get an exact answer. And when I do all of this, when I do 2,000 minus 168,000 over 88 and divide it all by negative 44, alright, there was a mistake. Uh-oh. Let's change this. What I did was I accidentally pulled this negative 44W over here, but I should have followed this equation, and I should have done plus 4W. Oops. So make that change. It's just plus 4W plus 4W. The neat thing is it doesn't make it that hard for us. Just change this to a 4W. And then here on the bottom, divide by a positive 4. There we go. All right, now, now when we do all this, we do 2,000 minus 168,000 over 88, and we divide that by 4, we get a positive number for our wind speed, which makes sense. We get approximately 22.727 miles per hour. So what we can say then is that our, oh, pardon me, let me move my papers out of the way here. We can say the wind speed was 22.727 miles per hour, and the speed of the plane was 477.273 miles per hour. All right, pretty interesting stuff. We'll see you in class tomorrow. Thanks for watching.